Let's discuss about the frequency shift gain. This is a digital modulation technique, which is defined as a process in which shifting of the frequency of the carrier signal takes place between the two levels, depending on whether it is 1 or 0. So let the two carriers be defined as Vc1 and Vc2 with frequency terms omega C1 and omega C2. Then the corresponding frequency shift gain is represented by Vm into Vc cos omega C1t when the given information is or the message is 1, or it is Vm into Vc cos omega C2t when the symbol is 0. Symbol means it is the information that can be 0. Symbol actually refers to the symbol actually meaning even also as the information. So this can also be a message. This can also be a message. So therefore what we can see here is if the given message is of the form 10110001, this is a digital message. This is plotted as a function of time t, and if the first carrier can be represented like this of frequency, the first carrier is of frequency omega C1, this is of the frequency omega C2, then the corresponding frequency shift gain is represented like this. So this is the point where the signal is maximum or the information is 1, so it is coming closer, it is compressed. When it is 0, it is wide apart. So the place where the information is high is closer short frequency, here it is wider or also known as rarefaction. And this is your compression. So when the signal is having information, then the frequency is compressed. When the information is 0, it is rarefaction. That is, it is going wider. So when the binary symbol is 1, FSK signal will have the carrier signal with the frequency omega C1, and when the symbol is 0, the frequency is centered around omega C2. It is achieved. So how do you know which one is selected? So the selection is by a selector circuit known as a multiplexer. Since there are two signals, you are using 2 into 1 kind of a multiplexer. So output of the multiplexer shifts between the two frequencies given by omega C1 or omega C2. Therefore, this is referred to as a frequency shift gain, and the corresponding block diagram is like this. Your Vc1 and Vc2 are the inputs. Your Vm will be your control input. So you remember you have in your multiplexer, you have control, CI control, and inputs, let us say A and B. So 0, 0, depending on what you choose. If it is 0, it will select. If it is not there, none. Then if it is 0, this has no meaning. Whatever be the inputs, it will not change. If it is 1 only, if it is 0, 0, it will select 0. 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. So like this, here also, your modulating signal is your control input. That will decide whether Vc1 has to be selected or Vc2 has to be selected. So this is a block diagram. Essentially, this is a 2 into 1 multiplexer that takes baseband message Vm at the control input. Vc1 and Vc2 are its inputs. So this is the block diagram. Alternatively, this can also be thought of as two ASK processes. What is ASK? ASK is your amplitude shift gain. So what happens is, so using omega C1 or omega C2, first ASK modulator shifts the control centered around omega C1. If it is omega C2, second AMSK, so whether it is first AMSK or second AMSK, they are both combined to give what is known as FSK. So this is the signal original message. So first one is centered around omega C1, second one is centered around omega C2. So combining these two is the signal is what you are getting. Then the corresponding M.Sc will be this plus this plus this. So you have a continuous waveform like this. So the better way of representing the same way, first one, this is centered around omega C1 and this is centered around omega C2. I have taken it from the textbook directly. So this is omega C1 and omega C2 is a FSK signal. C gives you so what is it? It is the original one. The B gives you first ASK modulator, the output of the first amplitude shift modulator. The second one is from that of the second ASK modulator. Finally, the D figure gives you FSK modulator signal. So far we have seen how to generate an FSK waveform. Now, how do you detect this? That is, detection is also known as reception. There are two ways of detection. One is a coherent detection, the other one is a non-coherent one. Let us see what is this coherent one. Coherent one assumes that in the receiver a copy of carrier signal is available. Carrier signal is available as a reference, and when it is passed through this coherent, that will be compared with the original carrier signal and accordingly it will be decided. So what do you have is an upper channel and a lower channel. You have here, this you are demodulating. So the input that is available is your FSK signal. This FSK signal is given to a multiplier. This will be multiplied with Vc1 dash and this will be multiplied with Vc2 dash. This is to differentiate between the original carrier signal. We are representing it with the primed quantity. Then this will send a signal upper. This will send a signal lower. This is sent through a low pass filter so that high frequencies will be passed on. Then what you get is S2 at the upper, S2 at the lower. These two are compared. The signal finally what you get will be proportional to Pm. So now let us see, this is the block diagram. How is it justified using the mathematical form? The incoming FSK signal is multiplied by carrier omega C1 in the upper channel and carrier signal with frequency omega C2 in the lower channel. The output of the multiplier in the upper channel will be low frequency message and ASK signal. This is a low frequency ASK signal. Here this is high frequency ASK signal. Okay. Then what happens is you can either get a sum of these two frequencies or difference of these two components. As you can see here, you have two components. So when you combine these two, you have frequencies which are summed onto the right side, and you can also have difference of the components onto the left. So when you say sum, it is omega C1 plus omega C2. If it is onto the left, it is minus. So in sum or difference can be written as omega C1 plus or minus omega C2. So this is what we get. So what happens here is the output of the low pass filter in the upper channel will contain baseband message during the intervals belonging to omega C1 and 0 during the interval. See, when it is passed through upper channel, it will have omega C1 and it is 0 when omega C2 is passed. Exactly opposite happens. The output of the lower channel will be passed on. So what happens if it is lower channel? It will have omega C2 passed and it is 0 when omega C1 is passed. So during this time it is 0. So upper channel will allow omega C1, lower channel will allow omega C2 and it is 0 at the remaining times. So both the outputs are connected to the comparator, and the output of the comparator will be high when the upper channel output is greater than the lower channel, and lower channel output is low when lower channel output is greater than the upper channel. Let me repeat, the output of the comparator will be high when upper channel output is greater than the lower channel, and low when the lower channel output is greater than the upper channel. So if lower channel happens to be greater, it becomes 0. If upper channel is greater, it is high, and vice versa. This way, baseband message is retrieved from the FSK signal. So in a pictorial way, this is a low frequency, omega C1 and omega C2. You have sum and difference components. So the output of a low pass filter will have baseband message during omega C1 and it is 0 during omega C2. Exactly opposite thing happens in the lower channel. So the outputs will be high when upper channel output is greater than the lower channel output, and it is low when lower channel output is greater than the upper channel output. So the same thing mathematically can be expressed this way. Vc1 dash is given by this, Vc2 dash is given by this. So the output will be Vfsk into Vc1 dash. This we have taken it from the previous expression for Vc1. So it is given by 1 plus 2 omega Ct. And during omega C2, it is S1 u, that is equal to omega C1 minus omega C2 plus omega C1 plus omega C2. So the output of the low pass filter in the upper channel will be given by this, and for the during this will be 0. So it is only due to omega C1 that you are getting, and this will be 0. So the filter output in the upper channel is proportional to omega m during omega C1, and it is 0 during omega C2. Similarly, when you consider S2 lower channel, it is just the opposite. Similarly for the lower channel, what will happen for a lower channel? It is Vm during omega C2. This is Vm during omega C2, and it is 0 during omega C1. So finally what you are getting is this, and S1L is this, S1L is Vc1 dash, and this can be written as 1 plus 2 omega Ct, and it is 0 for omega C1. So finally whatever you are getting is proportional to m, so the original signal therefore will be received. So in a graphical representation, this is first FSK, this is S1U. So when there is no signal, it is 0. When there is signal, it is high. When this is 0, this is 0. Now what will happen to the filter component? Filter component, since this is blocked, this will be allowed, this will be allowed, and it is proportional to the original signal. So, and S2, then this is passed, this is bypassed, this is bypassed. S2K, this is passed, say alternately S2 and S3. Finally the output is completely, what output you are getting is this is 1 0 0 1 1 0 1. So let me write the output here. Your output is 1 0 0 1 1 0 1. Let us see the corresponding input. Input is again 1 0 0 1 1 0 1. This is my input. So it is almost 4 D. Yeah, you are able to recover the signal back. So original signal is